Hi, I am Dibyendu Sardar. I am working with Professor Mikhail Tomja as a postdoctoral researcher. And thank you, Mikhail, for giving me an opportunity to present my current research work in this great talk conference. My title of the talk is a little bit different that I have sent. Uh, I have put here ultracold molecule-molecule interactions in excited states. Basically, I will discuss here two parts of this talk. Firstly, I will discuss ultracold calcium fluoride interactions, and then I will discuss ultracold metastable helium dimer plus metastable helium dimer interactions, both in their ground and excited states. So, okay, so excited state in atom-atom interactions are well studied last 20 years, and they are quite useful for the pathways to ground state molecule formations. They are quite useful to control the molecular interactions. Sometimes they are useful for state selective chemical reactions, and they might be useful for precision measurements for some ultracold molecules. And in this diagram here, I try to present here how the excited states are important for the molecule formation at the absolute ground states by a coherent stimulated Raman adiabatic passage. So, okay, now what about the current status about the molecule-molecule interactions in the current research field? So, actually there are very limited number of studies are available. So, first there is NAK interactions was studied by Arthur and Tice to understand the collision loss for these systems, both for the, and they have constructed a full dimensional potential energy surface for the ground state as well as in the excited states. And KRB also studied, but it is limited in the ground state. NARB plus NARB was also studied, but it is still limited in the ground state. And we are also studying the, we have also studied the CaF+CaF interactions for the ground state, ground singlet state, as well as the lowest spin polarized triplet state. So this is our motivation. From here we start the ultracold CaF+CaF interactions in the, to see the interactions in the excited states. So outline of the presentation as follows. So firstly, I will discuss ultracold calcium fluoride interactions, and to understand the source of the collisional losses for these systems. And then I will discuss ultracold metastable He2 in triplet state and He2 in triplet state interactions in fully spin polarized configurations. And I will then finally give some conclusions about these talks of my presentations. So why we consider CaF molecules? Actually, CaF is a polar molecule with 3.07 electric dipole moment. It has a magnetic moment around 1 Bohr magneton. Additionally, this molecule is a directly laser cooled molecule, and it can be trapped and cooled both magnetic and optical trap. And recently, not recently, couple of years ago, optical tweezer based approach has been used to study the collisional loss for this system, and they observed that the collisional loss approaches to universal limit both for the absolute ground state as well as the spin polarized states. So that's why we choose CaF molecules as an interesting candidate in our calculations. So initially we studied the ground state interactions between two CaF molecules, and we note that depending on the orientation of the electronic spin, when two CaF molecules approach each other, they can form the singlet channel, which is reactive in nature, and this highly exothermic reaction occurs, and they can also form the triplet channel, which is non-reactive in nature. So based on this observation, initially we constructed a 6-dimensional potential energy surfaces, and we study a bit of chemistry for these systems, and then we also studied the triplet surface too and calculate the density of the states, RRKM lifetime, etc. So now here I show some results about the excited states. So here is the Jacobi coordinate presentation of this system, and here we restrict our calculations under the rigid order approximations, and we consider the dihedral angle phi to be 0 for the simplicity. And we did multi-reference configuration interactions method, and with a very large active space to converge in the excited states, and basis set we used the correlation consistent basis sets. Okay, let's move on to the results. So here is the one-dimensional cut plots for the calcium fluoride interactions for the head tail orientations, and here is the head orientations, and this lowest black line represent the singlet A prime, and the red dashed is the triplet A prime state, and the importantly the blue dashed curve, which is shifted by 1064 nanometer of light, basically the triplet state, crosses the plenty of the excited intermediate states. And we note that the singlet A prime state always lower in energy than the triplet state, and this is also true for the T-shape geometry. And but there is a point here I want to mention that in the global minimum geometry of this system, actually the singlet triplet potential very close to each other, their energy are same, and this is very exception unlike alkali metal systems. So, and this is mainly due to the ionic nature of the Ca2F2 dimer. So then we calculate some kind of coupling for this system, like spin orbit coupling for the several geometries under rigid rotor, non-rigid rotor approximations. And it is the upper panel shows the spin orbit coupling, and lower panel shows the energy difference between these two states. And we note that the spin orbit coupling around the triplet potential of the lowest triplet potential is of the order of 5 centimeter inverse, and the energy difference between these two states is more than 1000 centimeter inverse. So therefore, the effective spin orbit coupling could be weak for these systems. So actually, then we discuss some plausible source of the collisional losses for this system for the spin polarized surface. So firstly, the molecules form a complex on the triplet potential and may vanish from the observations. This is one possibility. Second possibility, we know that the photoexcitation process. And third possibility is the non-adiabatic transitions from the non-reactive triplet to reactive singlet surface, resulting in chemical reactions. But in our calculations, we could not find any kind of singlet triplet crossings. So therefore, we may realize that the second mechanism, that is the photoexcitation, could be the plausible source of collisional losses, because there is a curve crossing with the excited states. So based on these observations, we have submitted a paper in Physical Review A, and this is currently it's online. So now I will discuss the second part of my talk, that is the interactions between two metastable triplet state helium dimers. Actually, helium atom is well studied in its metastable state around the beginning of the 20th century, and its BC was realized, Fermi degeneracy gas was obtained, SOF scattering length was measured experimentally. But what about the molecule of the helium molecule? Actually, when metastable helium atom interacts with the ground state of the helium atom, it forms the metastable helium molecule in triplet state, and its lifetime is around 18 seconds. And why this system is important? Because this can be useful for the high precision in spectroscopic measurements, may be useful for the directly laser cooling, because currently there are two groups are working for the laser cooling of these systems, and this system may be a platform for study fundamental physics and ultracold chemistry of these systems. So here I am interested about the dimer-dimer collisions in their maximum spin polarized state, because this system is very light system, only 8 electrons. Therefore, from the ab initio calculations, one can calculate the interactions very accurately. And to understand how complicated these interactions compared to the hydrogen-hydrogen system, because they are well studied hydrogen-hydrogen collisions. So, so here for this I did some quantum chemical calculations. I investigate the interactions both ground and excited states, and I investigate the global minimum geometry, and then I studied a little bit of chemistry about the stability of this helium dimer. And the not final goal, or then the next step will be the construction of the full dimensional surface, and probably the final goal is the quantum scattering calculation. I am not sure at this stage that how difficult it will be. So firstly, I optimized this tetramer under the coupled cluster calculations, and we found that this is a rectangular geometry with D2H symmetry. And note that here the binding energy of this tetramer or depth of the well is around 5000 centimeter inverse or more. And this binding energy is 2 orders of magnitude larger than the hydrogen tetramer, and this binding energy is comparable to the ground state of the alkali metal dimer. And this is mainly due to the larger polarizability of the metastable helium atom, which is again 2 orders of magnitude larger than hydrogen and comparable to the alkali metal dimer rubidium. Okay, then I want to show some one-dimensional cut plots for these systems. So here I actually calculated several one-dimensional cut plots, but here I present only one for the global equilibrium geometry as a function of the center of mass distance between the two helium molecules. And here you see that the ground state is not well separated from the excited states, and there are plenty of curve crossing occurs at the short range, and it introduces the multi-reference and multi-channel character at the short range. And the excited states manifolds are highly dense and they quite interacting to each other, and this and highly density of electronic states. And thirdly, if one can try to trap these molecules, they may be these molecules may show the laser-induced losses, because it is difficult to fit a laser for these kind of complicated interacting systems. Okay, then I will discuss a little bit about the chemical stability of this for these interactions, because when two He2 molecules meets on a spin polarized triplet surface, then trimer formation possibility is there, and this trimer may be either present in S equals to 2 state, that is in the quintet state, or S equals to 1, that is in the triplet state. So for this, here I have studied a little bit about the energetics of this study, and we optimize the trimer geometry for the global optimization, for the linear symmetric geometry, for the two linear asymmetric geometry, and for the triangular shape and some other geometries. And then we calculate the energy of the reactions, and each of these cases we found that the energy of the reaction is highly endothermic. So this indicates the chemical stability of this dimer on this surface. So based on this preliminary observation, so we are writing a paper, so it is under preparations. Now I think it is time to make some conclusions about this talk. So we have studied ultracold molecule-molecule interactions in both ground and excited electronic states. We calculate some spin-mediated coupling, and we propose a plausible, of course we did not make any dynamical calculations here. So we make some plausible mechanism behind observed collisional losses for this non-reactive spin polarized surface of CFCF. And for the helium project, we investigate the molecule-molecule interactions between two metastable helium molecules. We identified the global minimum and investigate the chemical stability of the helium dimers in its fully spin polarized surface. And now I want to thank to Professor Mikhail Tomja's group, and I especially thank to Marcin for several discussions with him. And I want to thank to John, because the calcium fluoride project was started from Gila when I was postdoc in his groups. Now this project is also ongoing. And I want to thank to PL Grid for the computation purpose, and National Science Center for the fundings. And thank you to all for your attention.
Thank you very much for this talk. Is it time for questions? So perhaps I ask briefly about the calcium fluoride collisions. I mean, is the conclusion that shielding is going to be absolutely necessary for evaporative cooling?
Yes.
Okay.
Yes. Yes.
Okay. I think if there are no questions, let's thank the speaker again.